everybody. I'm Thomas, I'll be your guide this afternoon. The next presentation will be in English. Der nächste Vortrag ist auf Englisch. We will see how to implement a classic computer, the Apple II, from scratch. Louder. Yeah, we will see how to implement a classic computer, the Apple II, on an FPGA, a computer chip that can be reconfigured using programming code to rearrange the hardware. Shemesh Shachar presents Nostalgia, FPGAs, and the Mad Personal project. Shemesh, you've got 30 minutes, including Q&A.
Okay, I'll talk fast. Hi, I'm Shachar Shemesh. I've been a software programmer for 40 years now, which means that I started really, really early. Okay, I'm old. And a few years ago, I remembered a game I used to play as a kid called Robot Odyssey. Anyone here familiar with it? Okay, it was a sort of an escape room game, so puzzles you need to solve. The trick was that you didn't use your own avatar in order to solve the puzzles. You had 3 robots which you could program by putting logic gates into to do what you want. So it was a sort of introduction to digital electronics. And originally it was written for the Apple II. Which I hope I don't have to introduce to the people who come to this conference, which presented a problem because if I want to play that game again, you may have heard, but this computer is not being produced anymore. So that's kind of a problem. Now, there are solutions. For example, that game wasn't programmed only for the Apple II. It also had a PC version shown here with its glorious CGA colors. So you could play on that, but there are other solutions as well. For example, you could use an emulator, which kind of got stuck here. But so this is Apple Win. I'm running on Linux, but Wine handles it okay. So if I press this button, you get the beep, and the drive works way too fast, but doesn't matter. And you get the game running. So you could do that. You could also, just a second, you could also go to robotsodyssey.online and run a JavaScript version of the game, since obviously I wasn't the only one who wanted to play it. It even allows you to save state to local storage on the browser and then export that to a file to save it or move it between browsers. So really nice implementation. And if you're really, really, really hardcore, you could even go on eBay. Yeah, that's the part that always gets stuck. You could even go on eBay and buy an Apple II. The prices here divide by 4 to get in euros. So it's not cheap. So you can buy an Apple II or 2 and actually play the game. But obviously, I did none of those things. Okay, I did all of those things. But I also decided to do something else, which was I started a new project under the name CompuSAR, where SAR stands for Some Assembly Required, where I decided to build my own Apple II clone from scratch, which brings up 2 pertinent questions. The first is, why? Right. And the second question is how. So I'll address the second one first. It's called FPGA. I'm hoping most of you are kind of familiar with that. I'll give a very quick explanation of what that is. It's magic. You type something on the computer, and then it turns into hardware. Poof. I don't think I have time for more details than that. It's magic. Personally, I used a board from a company called QM-Tech. So, and I found this board and I really fell in love with it because look at what it has. It has the actual FPGA. It has 256 megabytes of memory, which is for 8-bit computers, let's call it enough. It has HDMI output, which is, to me, was great because I think the legacy outputs, the composite and VGA outputs that everyone so love, are becoming more and more difficult to get proper devices for. Right? Even today, you can no longer get a new television that accepts RF running Spectrum or Atari 2600. So going to the forward-looking interfaces was a design decision I did. And it has I/O pins, which means that you can expand it for whatever it is that this doesn't have. So the goal was an Apple II on an FPGA. But then when I started, I figured, why stop there? At least for the computers from my childhood, which means the ZX Spectrum, the Atari 2600, the Commodore 64, and my personal favorite, which isn't an 8-bit computer, the Commodore Amiga. So those were the goals of the project. Not ambitious at all, which might bring the more familiar with the scene of you to ask, wait, that sounds familiar. Isn't there such a project already? It's called the Mister, and the answer is yes. The Mister does all of those, plus a bunch of other computers, some of which I've never heard of. And it already works, and it already does that. So why? Well, first of all, the joy of doing this is of doing this. But if I want to still give some sort of justification for the project, I can give you this. This is how much I bought the QM-Tech board for. No, there's no missing, and the decimal point is the correct point. That's $30. The Mister, before the pandemic, went for $370. So we're talking about a factor of 10 at least in the cost. So, and after the pandemic, prices rose and then lowered and rose again, and I don't keep track right now. So the goal shifted from building 8-bit computers on an FPGA to building 8-bit computers on a cheap FPGA. Ideally, I would like the final result to be sub $100, not including specific architecture customization. I'll talk about that a little later. So that is a pretty crummy FPGA. I've since changed the plan to something better. But if you know something about the FPGAs, it's 8,000 LUTs, 16,000 flip-flops, and 40 kilobytes of static RAM, which essentially is nothing. It's not enough for anything, which meant I had to do from scratch. So let's talk about what is a computer. And I'll give the caveat that the answer I'm giving here is correct for the computers done in the 80s. It's not really correct for computers done much earlier than that, and it's definitely not correct for computers done today. But in the 80s, a computer was a CPU, which is kind of the brain of the computer, and memory connected with a bus or two. So for 8-bit computers, usually you had a 16-bit address bus and an 8-bit data bus. Does anybody need explanation beyond that? Fine. Of course, this is a computer. It can run code. It can do everything a computer can do. But it's not a very interesting computer because it cannot interact with the world. In order to interact with the world, we need one more component, which is I/O. And the way I/O is implemented in 80s architecture is you take addresses that are meant for the memory and you steal them away to I/O component. So you say, okay, this is your memory range for most, we'll not talk about the Intel line of CPUs because we want to maintain our relative sanity. So you steal addresses. You say, if I'm accessing these addresses, then I'm no longer accessing the CPU, the memory. I'm accessing special units where merely reading or writing can change something. So I write to some address in memory, and all of a sudden, something happens on screen. Or I read, and I get a number that represents the last key pressed on the keyboard. Fine, so that's a computer. Where do we start? We start with the CPU. That's pretty straightforward. With CPU? 6502. That's the king of the 8-bit era. So what do? You write code in a hardware description language, which is something like HDL or VHDL or Verilog or C++. And then you run it in a simulator, which looks like this. And essentially, you're trying to figure out whether, given the instructions you gave, did your design change state the way it should have? So what you have here is we can probe anything we want. So we can probe any outside interface we want. So this is the clock. This is the address bus. This is the data bus, which is split into in and out because of the way FPGAs work. And then you can say, does this make sense? Does this operation make sense? And because this is a simulation, you can also probe some things which are not external. For example, you can check the state of the registers. So this is how you can do it. And it's a manual job that is error-prone and time-consuming. So I did the obvious thing, and I said, oh, I'll spend way more time creating a generic solution. So let me introduce you another computer I built. What you see here is Western Design Center 65C02 connected to 64 kilobyte of static RAM. Technically, that's 128, but you see this black line here that pulls an address line low, so that's 64 kilobyte. And that's a computer, right? CPU, memory, a computer. But not a very useful one. So you see all of those lines going out. They're connected to an Arduino Mega, which essentially can look at the entire bus and control pins. So the clock comes from the Arduino. And then the Arduino is connected to a PC, which can take the program, because this doesn't have any ROM. So memory is volatile. If you want it to execute a program, you need to load the program into memory somehow. So you compile it with a 6502 assembler. You use Python to talk to the Arduino, to talk to the memory, to load it into memory. And then you start running the program and record what the 6502 is doing each cycle into a file. And then comes the interesting part. You do the same thing. This Python program can do I/O. So you have a memory area where if you write to it, the test is done. Or you have a memory area if you write to it a number, that many cycles later, the interrupt signal will go low, will go active. So you can create a test program that tests not only the synchronous things, but also the asynchronous things. How do you respond to reset? How do you respond to interrupts? And then all you have to do is write a program that exercises the CPU for all of its aspects. Simple. And the nice thing is, if you then replicate this program from Python and you write it again in System Verilog, you can have automatic verification of your design within the simulator. So you load the program into the simulator, and you run it on your own CPU, and you have an infrastructure that makes sure that every single cycle you're doing the same as the authentic CPU. Which means that you end up with a design that not only is it cycle accurate, which means every instruction is executed in the same number of cycles as the original, it is actually bus accurate. So not only also every cycle your design does exactly the same as the original 6502. Of course, this isn't the original 6502, it's the Western Design Center one, but we have C++ emulation that emulates the transistor level transitions, and you can run the same test program, well, with the necessary adaptations on that, and get an authentic MOS 6502. So that's the CPU. Let's talk about the Apple II. Remember, we only have 40 kilobytes of RAM. But ROM is also the same resource. It's the same BRAM as the RAM on the FPGA. So essentially, we have the 6502, and we get 4 kilobytes of RAM and 12 kilobytes of ROM. Now, all we have to do is download from the internet the RAM, take it from a computer we definitely own, the ROM for the Apple II, load it into the design, and lo and behold, nobody's clapping. My fault. I'm sorry. Yeah. Okay. You'll notice that on this cycle, the read-write line is low, which means this is a write operation. The address is 494, and the data is A0. No, okay. 400 to 800 on the Apple II is the first text page. A0 is a black space. What this does is clear the screen. What you're seeing running here in the simulator is the startup routine of the Apple II clearing the screen. This is an Apple II booting. And don't feel bad about you not clapping. I posted this excitedly on Twitter and got the exact same response. People say, huh? So obviously, we need something more visual. So let's add I/O. We have UART. So what we can do is add a hardware component that 60 times a second scans the memory area between 400 and 800 and dumps it to UART. And then we can take anything that arrives from the UART and expose it at C000, which is where the Apple II exposes the ASCII of the last key pressed. We have 3 buttons on the board itself. One of them resets the FPGA itself, so it's not programmable. But one of the other 2 is labeled reset. Now it doesn't matter, it's just an I/O pin, but we might as well hook it up to the 6502's reset line. And the Apple sound system is kind of complicated with the 1 bit of audio. But I implemented it, but I don't have the speaker here, so I can't show it. But all that's left is we can take a console. Just a second. So we can take a console. We'll load a profile that uses the correct font, because we want it to look nice. And then we'll resize it to the correct size, which is 40 on 24. And now all we have to do is connect to the UART at 1 million baud. And then all I have to do is take the FPGA out of reset, and it doesn't work because and I get an Apple II booting. And because I have input, I can even program it. And now you can clap, please. Okay. Okay. Go back here. So let's talk about architecture.
Can I ask a question?
Yeah.
I'm sorry, get how you really learned what the CPU
Can you speak up though?
I didn't understand how you really extracted what the CPU does. I mean, only...
I did not, on the previous?
Yeah. I mean, that you see...
I'll get back to that in the questions part.
Yeah,
Okay.
sure, of course.
Sorry.
Just say.
I'll talk about it. Let me just finish this. So, architecture for the final solution goes like this. We have, on the left, we have the 8-bit side of the component. But what I'm afraid is that if I do everything as hardware implemented, I won't have enough room on the FPGA. And also, I have a problem, because like I said, I want modern interfaces. So I want USB keyboard, I want USB joystick. And in order to do that, doing that with an 8-bit CPU, and an 8-bit CPU dedicated to doing other stuff, and definitely doing hardware-only controllers for that, will fill up my FPGA. So instead, what I'm doing is this. All of the right side is a 32-bit machine. It's running some operating system that I wrote for it. And the idea is, whenever the 8-bit does, as long as the 8-bit is just executing code, it's executing code. Whenever the 8-bit is doing I/O, it interfaces into the 32-bit side, and it interrupts the RISC. And then the RISC says, OK, I know what that address means, and handles the I/O side of the things. And this way, a lot of the hardware that the 8-bit needs becomes software, of which doesn't cost me logic on the FPGA, it costs me memory. But remember, I have 256 megabytes of memory. So no shortage of that. Now, what you're seeing here, the gray areas are not yet written. And the green areas are ones that I wrote myself from scratch. Now, you might wonder, why on earth would I write the DDR controller from scratch? That does not sound like fun. It isn't. And the reason is, well, yes, Vivado has built a ready DDR controller, which you can just synthesize and add to your design. It's 4,000 LUTs. Remember, I have 8,000 LUTs total. And what I found out is that a lot of that logic goes to initializing the DDR itself, the chip. The initialization sequence is very long, and it's a huge state machine. But I already have a state machine in my design. You see up there at the top, the RISC-V? I can do that in software. And then I don't have to pay. And my DDR controller, remember, 4,000 for the MIG, for the memory interface generator. Mine is 200. Of course, things would have gone faster had I not taken on other aspects. In particular, not only did I do this project, I also opened a YouTube channel following this project, which is a whole different set of skills which I won't go into. It's called Some Assembly Required. If you really want to support me, I have a Patreon page, and all of the code is open source. All of it. github.com/compusar, and you can find everything I'm doing over there. Which brings us to the final question. Does Robot Odyssey work? No. A lot of work left. We don't have HDMI output yet. I had to redesign the 6502 4 times. But I'm beginning to overcome the overhead and start working on the things again. One last question to address. Why did I call this mad? What's mad about it? Well, the thing is, I'm trying to aim for production quality. I'm trying to aim for something that you can buy and it will work the way you'd expect a commercial product to work. Thing is, I'm aiming for sub $100. How many units will I sell? Let's say 5,000? How much work does it make sense to sell 5,000 units at $100? There is no economic feasibility to this project. The only reason it makes sense is because I'm not charging for my time. So, why did I do this? I did this because I wanted to learn how to program FPGAs. And the thing is, the best way to learn is by doing. And since it's hard, you better do something you're passionate about or you'll give up. Thank you. So we have a reserved question. So let me try and address it.
Is the question clear, by the way?
I'll pass the microphone for questions.
I will restate the question and then you'll say if I understood it, okay? You're saying, okay, you have a computer. How did you sniff what goes on the bus?
Yes, and not just on the bus, but behind, for example, if you have an instruction that adds or rotates, how would you sense that?
Okay,
just by looking at the
can't
signals
sense that.
is not enough.
You can't sense that. It doesn't expose state at that stage. But since I wrote the test program, what I can do is that every time after I add two numbers, I dump the relevant register as well as the condition codes. And this way I can make sure that the internal state updated correctly.
This way, as I understood it, this way, then you have your design and this as a golden sample which you can compare to each other. And you can check if your design is correct. But the question is, how do you get the design?
You write it.
Yeah.
Line after line.
Right, okay. So it's really manual job. Because this somehow, it reminds me, okay, in 2025, perhaps you can do something. Let this run a long, long time. Put a key AI over it, and then make it do this automatically.
Okay,
but
AI is a dirty word. No reason to be vulgar. But there are ways to make designs more modular and compact. And in fact, the RISC-V I'm using comes from an open source project called Spinal HDL. So Spinal HDL is a hardware description language that compiles to Verilog. And this is their demo project. And the reason I picked it is because it's very modular. You say, what do you want in your component, in your RISC-V, and then it generates Verilog that matches that. And so I think the RISC-V is around 300 LUTs. So it's really, really tiny because I don't need a lot. If I wanted floating point, it would be bigger if I wanted.
I have also some questions. So one thing is the 6502. I think this processor is, there are a lot of designs in VHDL in the internet. So I wonder why didn't you use ready-made designs, because there are so many. So your design must have an advantage, which is probably less space or something, because otherwise I wouldn't see any use of making it yourself.
Okay, I'll give, I actually had slides about it which I cut out because I didn't have time. So up until the last rewrite I did, the answer is no, there is no inherent advantage to what I did over the designs you find on the internet. In fact, one of the designs that everybody defaults to is by someone called Arlette Owens for a 65CO2, an open source core for the 65CO2. And the funny thing is, Hacker News picked up this project a couple of years ago, and someone asked in the comments, but why re-implement, why not take an existing design? And I started giving the long explanation, and someone else said, because the fun is in the implementation, not in the result. And then I looked who that was, and it was Arlette Owens. So generally, no. In fact, his design is actually tiny. The problem with this design, if I need to give a formal answer beside not invented here, is his design isn't cycle accurate. And his design is very compact but impossible to modify. It just, there's the microcode, and it just lists its numbers, which if you want to change, you need to know really what each bit means, which is kind of difficult. In the latest design, in the latest redesign I did to the 6502, I did do something that doesn't exist in any other design on the internet. It doesn't make it better, it just makes it better for this project, which is I run the 6502 at the same clock speed as the RISC-V and on the same type of bus, so using a synchronous bus, because the original 6502 uses asynchronous bus. And then I just use the synchronous bus back pressure mechanism to slow it down to the 1 megahertz it needs to run at. And that means less clock domains inside the design, and it means that it's a better fit. It's easier to manipulate things.
Okay, then the next question. So when I look at this RISC-V, let's say we take a Pi Pico, either the old one or the new one with the RISC-Vs. So this processor, I think, would be from its calculation power sufficient for this kind of project, because it's dual core, so it could do the graphics and could also do the calculations. So I would see more sense either to have the whole system in the FPGA as a full design, but a mixture of both worlds seems for me a little bit critical, because I mean, then I would fully go on the RISC-V system without any FPGA.
Okay, so this throws back to the previous talk we just had about the difference between re-implementation and emulation. So if you're going to put in a modern CPU and use software in order to make it behave like a vintage computer or like a retro computer, then what you're doing is emulation. And everyone have different opinions about this, but the thing I really wanted this design to be able to do is to allow me to expose a bus and connect original expansion cards designed for the Apple II, the Commodore 64, whatever, to that bus and have it work. And that requires an actual, even if in FPGA it requires an actual CPU behind it. So it's a matter of taste. The hybrid approach you're offering wouldn't work at all, because it wouldn't work for the same reason I'm not using an FPGA with, like the Mister. The Mister has an FPGA that has a built-in ARM core in it. So it has an ARM core that loads Linux and an FPGA. And it allows it to do things like put up a menu and then have that menu select which core you load, which this will not be able to do. It will be able to reprogram the flash so that after a reboot it will be a different core, but it will not be able to switch cores on the fly. The reason I didn't go with a hybrid FPGA CPU chip is cost. They're expensive. If you start with, I want the bill of material to be lower than $80, then a lot of those things that people in our community do all the time, because they're great, they save you a lot of time, they mean that you don't spend 4.5 years on a project and still only have text mode. But if you're looking at it as I want the end product to be cheap, then they don't get you over the finish line.
Any other questions?
Don't sound desperate.
No, it's totally fine.
So usually the people have different design goals. So one design goal could be cost, or one design goal could be cycle accuracy, or something like this. So there could also be another solution. You could have two of your boards, which were, I think, at $23. And then one of this board can be the RISC-V, because there are very low number of LUTs, usage RISC-Vs, and I think a board of this would be
But
sufficient.
I can fit it inside a single FPGA. Why would I want two FPGAs for that?
So you will skip the RISC-V.
No.
Then,
One FPGA
yeah,
with all of this.
including the RISC-V.
Yeah,
This 80,000 LUTs FPGA you have.
8,000.
8,000, yes.
Yes.
Because I thought the RISC-V you have there, the orange one, you will use as an external.
The only thing that makes it orange as opposed to green is the fact that I didn't write it. I used an existing implementation.
Then it's clearer. So my questions are obsolete, because I wondered why you are not doing the whole system in one FPGA board. So then, okay.
The answer is that I am. You can't do the cost with more than one FPGA. It will not. Thank you very much. The board is here. It looks like an FPGA board. So,
Thanks a lot, Shemesh, and thanks for all the questions. Next presentation will be at 3. See you then.